So my name's John Devon, and I want to welcome you to the Distinguished Speakers in Software Engineering series. What we're trying to do is bring in people from outside the company to generate thought and idea and discussion around how we can do a better job at engineering our products across Microsoft. Inside the company, you probably know about the Engineering Excellence Initiative, and this is the way that we're partnering with Microsoft Research, not just to have us inside the company figure out better ways to do things, but also try and get the best ideas from outside the company as well. Today we have Steve McConnell from Construct speaking to us, and in a few weeks we'll have Peter Newman from SRI International's Computer Science Laboratory come speak to us, and we actually have a pretty impressive slate of people coming in, and I hope we can learn a lot from them. It's exciting to be able to get these caliber of people to come and visit and share their ideas with us. I'd like to introduce Steve. He's the chief software engineer at a company in Bellevue called Construct Software. And they do a lot about helping companies with their software engineering practices. Most people may know Steve from the Code Complete books, which are very excellent books on software engineering and programming. Steve is a lead for the construction knowledge area of the Software Engineering Body of Knowledge project. Steve has worked on software projects at many companies, including Microsoft, Boeing, and other Seattle area companies. As a very accomplished author in the field, he's written a book named Rapid Development in 1996, the Software Project Survival Guide in 1998, and the Professional Software Development in 2004. He has twice won Software Development Magazine's Jolt Excellence Award, and he's also the lead developer of SPC Estimate Professional, which won a Software Development Productivity Award. In 1998, Steve was named one of the 3 most influential people in the software industry, along with Bill Gates and Linus Torvalds. With a bachelor's degree from Whitman and a master's from Seattle University in software engineering, I'd like to introduce Steve McConnell. Thank you, Steve.
Thanks, John. Well, it's very nice to be here to talk about Code Complete. It was not too far from here that I was working on the original manuscript for Code Complete. So now, 13 years later, it's nice to kind of be back to talk about Code Complete 2. Now, one of the problems when you write a book called Code Complete, or rather Code Complete, and then you go to work on a second edition is you have to answer the question, well, what about that first edition? Was it complete or wasn't it? And so we kicked around some various possibilities for titling the second edition. We thought maybe we should call it Code More Complete or Code Really, Really Complete. And, of course, you all know how effective Microsoft's marketing department is, so they thought maybe we should ride the wave of a similarly titled book and call it something like Da Vinci Code Complete. My favorite suggestion was Code Complete. This time it's personal, but we ended up, of course, just calling it Code Complete 2 or Code Complete Second Edition, which has been out since June. The work on the second edition has given me an interesting perspective on seeing what's changed and what hasn't changed over the last 10 years in software construction. In 1993, my attempt was really to try to capture the part of software construction knowledge that wasn't likely to change over time, the more principles-oriented knowledge that would be more stable. And for years, people have been writing me and saying, hey, Steve, do you have any plans to update Code Complete? And I would respond and say, well, actually, no. I think it's pretty much up to date except for some of the cosmetics of the programming examples. And I think 95% of the content is still relevant. Well, since I've now gone through all that content, I think I have a little bit of perspective on how relevant it was or was not. And I'll share some of those thoughts with you as we go along. The scope of the work for the second edition was really pretty deep and wide, as it turned out. I had a team of 4 developers who worked for me go through a formal inspection on the entire first edition. all 900 pages of it. And we actually did the full inspection process, and that was quite interesting. We found an amazing number of defects, and you'd think for a book that had been out there for 12 years, that had gone through extensive peer review the first time around, and that had literally a couple hundred corrections made in 27 printings, that there wouldn't be any defects remaining, and yet we found a few hundred defects as we went through the formal inspection process. So that was pretty interesting. The book has about 500 programming examples, which originally were in Pascal, C, and BASIC. Those have been updated to more modern languages: Java, Visual Basic, C++, a little bit of C#. We added new chapters on design, on classes, on defensive programming, on collaborative construction practices, and refactoring. The first edition was written when object orientation was well established in research circles, but just kind of beginning to make its way into practice, and so I really didn't talk about that very much, since the focus of the book is on techniques that have been shown to work in practice. So we've integrated the discussion of object orientation and web development throughout. Of course, there's been an explosion of good books and articles in the last 10 years, and so further reading has been updated throughout. And then the nice thing about publishing a book today as opposed to 1993 is we've got this very nice tool called the web, and we have a pretty extensive website up with probably a couple hundred pages that give lots of pointers to further reading, and over time we can keep those up to date even as the book stays exactly the same. So the scope of the work gives you an idea of just how deeply I was able to get into this construction body of knowledge for the sake of putting together the second edition. So what I'd like to do this morning is talk about some of the worst construction ideas of the 90s and the 2000s, maybe try to pick out some patterns there, and then spend a little bit of time talking about what has improved over the last 10 years, and conclude by talking about 10 realities of modern software construction. And the slide says if we get to it. I promise you we will get to it. So what are some of the worst construction ideas of the 90s and the 2000s? Well, here are my nominations for the worst construction ideas of the 90s. Number one, code and fix development. That's been a bad idea for a long time. It was a bad idea in the 70s, bad idea in the 80s, an idea that didn't really work very well in the 90s either, and that was one of the practices that the first edition was intended to help avoid. Second, worst idea number two is the idea that we could do all our design up front before we began actually writing any code. I think at that time in the industry we had a lot of industry pundits who wanted us to dot every I and cross every T on our designs before we wrote any code. I think that that wasn't working at the time, and as the years have gone by, it's become even more clear that that typically doesn't work very well. We certainly can design critical sections up front or have an idea of what the design will be, but the idea that we can do literally all the design up front, I think, has just proved not to work very well. Worst idea number three, design for speculative requirements. The idea that not only could we create 100% of the design up front for the requirements we know about, but we can create even more design for requirements that might emerge at some point later in the future. I think that tended to result in over-designed, bloated systems that actually didn't meet the requirements they knew about very well, much less the speculative requirements later on. Worst idea number four, the idea that components will solve all of our construction problems. And I think this points to a recurring pattern in the software industry. We get an idea that's a good, useful, valuable idea, but then we overextend it thinking that it's going to solve all of our problems. And I think components are a nice idea, but the idea that we're no longer going to have programmers, we're just going to assemble programs out of pre-existing components, I think was not a good idea on its face. I'm surprised in a way that it got as much attention as it did. Worst idea number five, automatic programming. This chestnut has been around at least since the 1970s. There was at least one paper published in the 1970s explaining why, for theoretical reasons, this really wasn't possible. And I think that we have continued to hear claims every few years since then that programming is going to go away and we're never going to have to program again. Of course, this claim first came about with the emergence of Fortran, when scientists were no longer going to have to write computer programs. They would just write formulas, and programming was going to end. And I think what we really did is simply change the sort of lexical toolkit that programmers have to work with. But this need to take vague ideas and translate them into very precise statements in some notation or other, I think, is just not going away. Worst idea, number 6, is uninformed use of the waterfall model. I think there was a grain of truth in the waterfall model. As a response to code and fix, I think it was a step forward. But as people used it in an uninformed way and tried to take it extremely literally, it didn't work very well. And finally, I think calling everything object-oriented was one of the worst ideas of the 90s. We got into object-oriented, started with object-oriented design and object-oriented programming. Then we got into object-oriented analysis and object-oriented testing and object-oriented usability design and object-oriented reviews and object-oriented goofing off. And I think it's just taking a good idea too far. All right, so those are my candidates for the worst construction ideas of the 90s. As we go through the worst construction ideas of the 2000s, you may notice some similarities. Code and fix, again, didn't seem to go away. Still a bad idea. No design upfront programming. The pendulum has now swung all the way to the other side. This isn't working out any better, as far as I can tell, than all design upfront did, although at least it eliminates the bureaucratic overhead of creating all the design upfront, replaces it with the bureaucratic overhead of fixing all the design that you didn't do. Planning to refactor later. I think refactoring is a good idea, but I think refactoring as a strategy, that we are not going to do any design up front, because we're just going to refactor our way out of it later, is one of the worst ideas currently floating around. Worst idea number 4, the idea that offshore outsourcing will solve all of our construction problems. It's interesting to me. I think that here the perception among the companies that got into this some time ago and have good experience with it is quite different than the perception in sort of the mass media or rank and file companies. The companies that have been at this longer have a pretty good understanding of a pretty narrow range of applicability of this practice, which is quite out of step with what I think industry at large is still fairly naively believing. Worst idea number 5, automatic programming. Again, this is an idea that just will not go away. Worst idea number 6, uninformed use of extreme programming. Is there similarity to uninformed use of the waterfall model? Absolutely. I think the idea that we can say that we're doing the waterfall model, or we can say that we're doing extreme programming and sprinkle the extreme programming holy water on the project and expect that in some way that's going to make the project runs better, is really not a step forward. I think that informed use of the waterfall model is going to be better than uninformed use of extreme programming every time. And I think informed use of extreme programming is going to be better than uninformed use of the waterfall model every time. So what is the common denominator there? Well, it doesn't have a whole lot to do with the methodology. It has to do with how well informed people are and how good the skills are. Finally, I think the last worst idea is calling everything agile. I think that that's about as bad as it was with object orientation, to the point where I don't know that the word really, at least in common usage, has any real meaning anymore. I think it's become a synonym for modern or contemporary practices with no real meaning beyond that. So those are my candidates for the worst construction ideas of the 90s and the 2000s. The list is obviously somewhat contrived for purposes of this talk, but if you look at the correspondence between the different ideas across the 2 decades, I think it's interesting, even as a contrived exercise, that it's possible to create a list where there are such strong parallels across the decades. And if you look at each of the pairs, it actually looks like we've got kind of the same themes going year after year. And I think that speaks to a fundamental aspect of software development that I'll get to toward the end of the talk. If you don't mind, I'd rather hold questions until the end with a group this size, unless it's a clarifying question.
What instances of automatic programming?
Automatic programming has been the idea that we can just describe the problem in natural language and then the program will write itself. An idea that's been around for a long, long time.
But that's very much a theoretical idea. I mean, I don't really see people seriously trying to do this. Whereas the other ones people are trying to do are doing. So I just wonder why you put it there.
I'll answer your question, then I'm going to ask the rest of you to hold questions. I disagree with that. I think the whole case tool movement in the 80s and 90s was an attempt to achieve automatic programming. A lot of the efforts with the 4GLs were attempts to achieve automatic programming. we still hear claims fairly recently about the need for programmers going away in the near future. So I think the trade press I'm reading might be a little different from the trade press you're reading. The articles I'm reading are maybe different as well. But there definitely are people out there who are still pounding this particular drum. Okay, I'd like to move to the second part of the talk, which is a decade of advances in software construction. One of the nice things that I saw as a result of going through an end-to-end modification of the construction knowledge area in Code Complete is, in fact, things have improved significantly in 10 years. There have been some advances that, if you don't really take a step back and compare differences 10 years apart, you might not be aware of. And interestingly enough, after I wrote Code Complete, the first edition, I basically didn't read it again for 10 years. And my thinking had been evolving, the software world had been evolving, and somehow I kind of expected that the ideas in the book were evolving as well. But of course, when I went back and read it 10 years later, it was almost like a time capsule of software practices in 1993. And so I think we have seen some good advances. One of the advances I would point to is that when I wrote the book back in 1993, one of my pet peeves was that it seemed like every software organization I went into had a server named Gandalf or Frodo. And so the first advance is that with the theatrical release of Lord of the Rings, now every company has a server named Gandalf and Frodo. All right, the real first advance, number one, is that I think design has been raised a level. And this is an important advance. I think that if you look at the history of software construction, one of the major influences on how it's advanced has been the tools we have to create sort of thought aggregations or chunks at larger levels. Initially, we only had assembly language statements, and then we had macro assembler, and then we had third-generation languages and the concept of the subroutine. And we got to create these little thought units called subroutines. And then we got thought units of classes. And that really is a big advance. We now have this larger thought unit. Forget about object orientation or whether it models any real-world object. The idea that we can now think in abstractions that are larger than an individual subroutine, I think is a major step forward. It allows us to chunk things better and better manage more complex designs. And with some languages now supporting the concept of packages, I think that really is a nice next step where we can create the next larger level of aggregation. I think it's interesting if you look at what the real contribution of object orientation has been. I think you could at least make an argument that it hasn't really been objects per se. It has been advancing the level of aggregation to the next higher level. Okay, major advance number two, I think, is widespread use of the daily build and smoke test. When I wrote the first edition of the book, to my knowledge, Microsoft was really about the only organization that was making routine use of something kind of sort of like the daily build and smoke test. Some groups were using it more consistently than others. I think now we see organizations using this in a pretty widespread way, and it's nice because I think that it institutionalizes the idea of incremental integration. If you read the computing literature of the 1970s and 80s, you'll find that integration risk is often cited as a major cause of project failure. People would develop the program in pieces, bring them all together at the very end of the project, and practice what was called Big Bang integration. And it was called Big Bang integration because when you brought the pieces together, they tended to explode. And a lot of times projects failed at that point. Daily builds help to eliminate that problem, which was one of the more common problems decades ago. I think there are other benefits too, including improved project visibility, improving the team morale as the team sees the software come to life, improved customer morale because the customer can see the software. So I think this is definitely a major advance. Major advance number three, the widespread use of standard libraries. I think that one advance is that over the years, good programmers have always had personal libraries of code. Years ago, I worked with a programmer who was quite proud of the stack of, or this a couple of trays of punch cards that he had accumulated. He had a real paper library, and he could put together any program in his environment in half a day or so because he had a really well-honed set of punch cards that he accumulated over about a 7-year period. So I think we've always used libraries to some degree. The nice thing about having standard libraries, though, provided with Java or C++ or .NET, is that now not only can we make use of libraries, but we can communicate in a shorthand way. Again, it's that higher level of aggregation idea. If I tell someone that I'm using a certain library function because it's standard, they probably know what I'm talking about. Whereas if it's just my personal library, it doesn't really help me communicate with other programmers. But if it's standard, it does. So I think that's a very nice advance. Major advance number 4, I think, is Visual Basic. And I think I have to give Microsoft credit where credit is due on this point. I had been working in Smalltalk for about a year prior to I'd been working in Smalltalk for about a year, and then I took some time off from anything like that, and then Visual Basic came out a couple years after that. And my initial reaction to Visual Basic was, wow, this is kind of what Smalltalk was trying to be. And I like that a lot. I think the innovation of being able to manipulate things on the screen through a little bit of visual programming was very nice. I think Visual Basic has to get credit for being the first development environment to really support the widespread production of programming components for a mass market, and that was a big advance as well. And as I looked at some of the advances in Visual Basic for VB.NET, I would make the claim that VB is really the only major language to have learned some of the syntax lessons that Ada tried to learn, but then didn't really, it wasn't successful enough as a language, including things like the way the case statement is structured, the way the other control statements are structured, and so on. If you look at C++ and Java, for example, the switch statement structure is a really clunky structure. You have to enumerate each thing that you want to test individually, and then you have to manually put in a break to tell it that you're done. That's really, in my mind, a dumb structure for a switch statement. VB actually has, you can put ranges in your case statement. You don't have to put in the break. And if you think this is a minor point, you'll realize that in the 1990s there was a phone outage on the East Coast that wiped out the phone systems for the entire eastern half of the U.S. for about half a day. And the reason for that phone outage ultimately was traced down to a misplaced break statement in C programming language. So, you might think that these details don't really matter, but that sort of error would have been impossible in Visual Basic, given its structure for the case statement. So I think this is maybe not the biggest point I'll make this morning, but I think it's still a notable point. And then the integrated environment, I think, was a nice step forward as well. Now, having given Microsoft some credit, now I've got to take some away. I think advance number 5 is open source software. And I think this has been a big advance in a couple of different ways. One is that I think that it is possible in some environments, and product-oriented environments tend not to be those environments, but in some environments where you're not as concerned about polluting your intellectual property, it can be a real aid to programmers in speeding up their development. It also reduces barriers to making code available to others, as you all found out here with some of the Windows 2000 source code. Not really open source, but through the web. And I think the nice thing here is that when I wrote the first edition of Code Complete, it was really hard to find major chunks of code that you could point student programmers to or other programmers and say, here's an example of some code, either good or bad, but that's real production code. And now with resources like SourceForge, we actually have a pretty good ability to point programmers to major chunks of code, both good and bad. And I think people tend to learn best, especially programmers, learn best by example. And previously, we didn't really have examples that you could look at. Everything was proprietary. Now, we at least have some decent examples. And that, I think, improves people's ability to read code. And I think it sets up a nice community. Again, in larger organizations like this, you don't have to worry too much about a sense of community with other programmers. But an awful lot of programmers are out there working in 1- or 2-person programmer shops. And for those people, being able to have a sense of community, even online, I think is a huge step forward. Major advance number 6, I think, is the web. And here I mean mainly for research. The availability of FAQs, the availability of discussion groups, the ability to search for answers to your questions, I think really has made a lot of things easier. Back when I started programming, typically your only available references were paper references. If your company was rich enough, maybe you would buy one of the commercially available online language references. But I think mostly you were kind of stuck looking at books. And I think today the ability to get answers to questions so quickly, I think, is a nice step forward. Advance number 7, widespread use of incremental development. We talked a little bit about this in the context of daily builds, but I think more broadly, the idea that we do a little bit of requirements, do a little bit of design, do a little bit of construction, and then repeat that, I think is one of the major advances. I talked about this in the first edition, but at the time I talked about it, it really was more aspirational than a description of what was actually occurring. Leading organizations had been using it, but not very many of them. But by the time we get into the 2000s, I think incremental development, as popularized by a number of methodologies, whether it's Scrum or extreme programming or DSDM, or just sort of the general osmosis of being in the industry, I think this is a much more widespread idea in practice today than it was 10 years ago. Advance number 8. I think is test-first development. This is an idea that I think is not currently in widespread use, but I think has the potential to provide as much benefit as daily builds do by shortening the time between the time that a defect is introduced and the time that a defect is detected. And if we can detect that defect essentially as soon as the code is written and the test case is run, then that really enables us to find that defect very close to the time it's created when the code is still fresh in our mind. Typically, it could be something that's an obvious oversight. We can correct it easily. I think this is a major advance. I think it also increases personal discipline, forces people to think through what they're going to write before they write it at a very detailed level. And I think it's a nice complement to the daily build and smoke test. So I think this is a very nice practice. Now, the next 10 years will tell whether I'm right about this one. Most of these are descriptions of what's actually happening. This one is a little bit more forward-looking, saying, I think this is a great idea, but I don't really see this in widespread use at this point. Major advance number 9, and we have 10 of these major advances, by the way. Major advance number 9 is refactoring as a discipline. Now, earlier I said refactoring as a strategy I thought was one of the worst ideas of the 2000s, and I think that's true. But as a discipline, I think refactoring is a major step forward. Whereas before we might have had sort of a vague feeling of what we might do to affect a set of changes to an existing code base, refactoring gives us more of a systematic approach to making those changes in a disciplined way when those changes are needed. As a look-ahead design strategy, I don't like it, but as a disciplined way of reacting to necessary changes in design, I like it very much. My complaint about refactoring doesn't have a whole lot to do with refactoring as Martin Fowler described it, but has more to do with how refactoring actually gets used in practice, which is far more often than I see refactoring used in the way it was intended. I see programmers saying, I'm refactoring my code, when what they mean is, I'm fixing my code. And that's not refactoring, that's just fixing bugs, and I don't think we should try to dress that up by calling it refactoring. Major advance number 10, I think, is faster computers. Computers really have become amazingly fast in the last 10 years. And how fast are they? Well, one thing you could say is they're so fast now that it takes 2 halt instructions to halt the CPU. Another way to look at it is that according to extreme programming, computers are so fast it now takes 2 programmers to keep up with the computer through pair programming. That's either not funny or you don't get it. I don't know. I'm going to choose the latter interpretation. But I think when I wrote the first edition, I have 2 chapters on performance or on optimization at the code level in Code Complete. And there are several dozen benchmarks. And so one of the things we did for the second edition was to update all of those benchmarks for use in modern languages and on modern computers. And whereas in the first edition, to get measurable results, we were running most of the benchmarks, or to get consistently measurable results, we were running most of the benchmarks 500 times or 1,000 times, or in some cases maybe 5,000 times. In the second edition, to get measurable results on today's desktop computers, we were running these tests 1 million times, 10 million times. And at some point, I think you have to ask the question, if you have to run a test 10 million times to get measurable results, is it really measuring anything that anyone cares about? And I think the answer is no. I think it's measuring something that doesn't matter in most cases anymore. And I think that's good news for us. I think what it means is that we don't really have to be very concerned at optimization at the detailed coding level anymore. We can focus on writing code with maximum clarity and move our optimization considerations up to the design level rather than fixating on it at the detailed coding level. And I think it has, so that's an implication for optimization. An implication for programming languages is that it allows us to use programming languages that are much slower but still work fine on today's computers. For decades, the research has been pretty clear that programmers tend to be more productive in interpreted languages than they are in compiled languages due to the quickness of the feedback cycle. And for decades, the problem has been if you write the program in an interpreted language, typically that language doesn't have the performance that you need to actually release the program. But today, I think it actually is practical, maybe not in this environment, but in many environments, to write major chunks of your program in an environment like, or in an interpreted language like Smalltalk, or in a scripting language like Python, and release it that way. Maybe you could, if you did have major performance issues, you could write small pieces in C++ or Java, but you don't have to do that with the overall application. That allows you to get the best of both worlds, more productivity and performance that's perfectly acceptable. So I think there have been, to summarize, some significant advances over the last 10 years. And if you've been around the last 10 years, it's easy to kind of take them step by step and not realize just how far we've come. So with that as background, I'd like to turn now to the final section of the talk, which is 10 realities of modern software construction. And I think that while some things have advanced, I think some things have remained pretty stable, and I would anticipate these remaining stable for a long, long time. The first, I think, is that construction is a legitimate topic. In the first edition of Code Complete, I published a diagram that looked like this. My purpose in publishing this very traditional, sequential, linear view of the software lifecycle was not to say, I think that the software lifecycle has to be sequential and linear. My purpose was to say, hey, look, here's a well-recognized picture of the different activities, and I'm going to focus on the one called coding and debugging. And this kind of backfired a little bit. As a result of this, I think people kind of interpreted me as having a more linear view of software development than I do. And in fact, I was looking at a news group posting last fall, and I saw a posting from Kent Beck, the author of Extreme Programming, where he actually accused me of being a phasist. And at first, I thought I'd misread it. I thought maybe he'd misspelled fascist, but no, he actually had accused me of being a phasist. So in the second edition, I now have a diagram that looks like this, and I defy anyone to look at that diagram and accuse me of being a phasist. I think that the key point here is that the fact that we identify a specific activity does not necessarily mean that that activity has to be the same as a phase. And I've got here activity not equal to phase. And for those of you who do VB, it's different notation. And that's significant. I had Scott Myers review the manuscript, and Scott saw that greater than, less than sign, and he didn't know what that meant. He had to send me an email saying, what's this funny symbol? I think you've got a typo. And so Scott's always been very proud of the fact that he does C++ and that's it. And I guess that's really true. So I think that the fact that we can talk about construction as a specific activity doesn't mean we have to think of it as a phase, but I think it's tremendously useful to identify different kinds of activities. And that's one of the issues John, in his introduction, mentioned my work on the Software Engineering Body of Knowledge project, or SWBOC project. And I think that one of the problems people have had with the SWBOC is looking at the set of 10 activity areas that are identified and assuming incorrectly that that means that the SWBOC thinks that there are 10 phases. I think that's just a flat misinterpretation of what's being accomplished there. I think being able to talk about things in a distinct way and saying, okay, we understand there are gray areas between construction and design and requirements, but it's kind of, it really is inhibiting to not be able to at least talk about the core of each of those areas and the distinct properties and the characteristic activities of each of those different areas, acknowledging that there's some overlap and some gray area. I think reality number 2 is the idea that individual variation is significant. This is one of the most replicated results in software engineering research. Since the first paper on this was published in 1967, researchers have continued to find differences on the order of 20x between individuals at similar levels of experience. The first study looked at individuals who all had at least 7 years of professional programming experience and still found 28 fold differences between the productivity of the best and the worst person in that group. Researchers have found these variations across basically every software development activity you could think of, but certainly including coding, debugging, the speed at which people find defects, the percentage of defects that they find, how many bad fixes they inject as they also try to inject good fixes, the quality of the designs they produce, and so on. So I think that recognizing that individual variation is significant really is one of the key realities that we have to look at, and practices that set themselves up to leverage the capabilities of people who are on the 10x or the 20x side, I think tend to be good practices. Practices that assume that we're going to drag everybody down to the lowest denominator, I think, tend not to work very well, and tend to be resisted by the best contributors, which is exactly the opposite of what you want. Interestingly enough, if you look at the key skills that I think make up a really effective programmer, I think it includes things like being able to do a good job of design, fleshing out errors and ambiguities and requirements, writing high-quality code, being good at reading and reviewing code, being good at integration, debugging, unit testing, and teamwork, and having up-to-date knowledge and expert knowledge of tools for all of the above. The interesting thing about this list, in my mind, is that at this level of abstraction, this list has not changed one bit in the last 10 years. I think that at this top level of abstraction, the skill areas are exactly the same. Now, if you go into the details, of course, the details below each of these bullet points has changed quite a bit. But I think it's interesting that at this level of abstraction, not too much has changed. Modern reality number 3, I think, is the idea that personal discipline continues to matter in software construction. I think one of the things that I think is interesting on this point is that we had a Watts Humphrey come and talk to a group that I run, an executive, technical executive group, and Watts Humphrey, the founder of the CMM, personal software process, and so on. And one of the things that Watts emphasizes, of course, is discipline. He has a very thick book called A Discipline for Software Development and Software Engineering. And so discipline is something that's big to Watts. But one of the other things that struck me was that Watts made the comment over and over and over again that you have to stand up for what you believe in, and if somebody's trying to get you to do something the wrong way, you have to do the right thing. And he never used the word courage, but in every way that you could sort of triangulate that area of courage without actually saying the word, I think he did. And on the other end, what usually would be considered the other end of the spectrum, we have Kent Beck with Extreme Programming, who specifically talks about courage as one of the important values in extreme programming. And I think extreme programming has also been characterized as sort of a high ceremony, high discipline kind of practice. So it's fascinating to me that we have two people who would usually be considered to be on opposite ends of the spectrum, both emphasizing the importance of discipline and courage. And so there's an interesting convergence there. Where does discipline matter? Well, I think in refactoring, the idea that we can practice it in a disciplined way, not use it as a cover for sloppy practices, but as a disciplined way to make high-quality code changes. Prototyping, the idea that we're just going to prototype the minimum amount of work that we need to answer a specific question rather than straying into actually trying to write the software. That requires a lot of discipline. Optimization, the idea that we'll focus on writing the highest quality code we can first and worry about optimization later, I think is an area where discipline tends to fall down. And the idea that we're going to try to keep a lid on unnecessary complexity and try to strive for minimal designs that meet the current requirements in a minimally complex way, I think that requires a great deal of discipline too. So I think personal discipline matters really in many, many different kinds of construction activities. Modern reality number 4, focus on simplicity tends to work better than a focus on complexity. And I think it's interesting. And my company has a pretty active consulting business. We look at a lot of organizations every year. Our experience in the consulting work we do is pretty consistent with what we find in other published industry surveys, which is that projects usually fail, number one, for requirements-related problems. And so that's not really a detailed technical issue. Second most common cause of project failure is poor project planning, poor project management. Again, not really a hard technical issue. So projects do not most often fail for hard technical reasons. But when they do fail, what we find is that they fail due to the fact that the code base has gotten brittle and complex and overly interdependent. We use words like brittle or barnacled or spaghetti code. What that means is that the complexity has gotten out of control. Nobody on the project can really understand what the program does anymore, and so it becomes unsafe and destabilizing to make changes in the face of an overly complex design and code. And I think what we tend to find works better is projects that focus on simplicity, making the code as readable as possible, as understandable as possible, tend to scale up better than projects that focus on clever solutions or overly complex design. And one of the ways that I've characterized this to myself over time is that you often hear people arguing about issues based on right time convenience. And I've concluded over the years that right time convenience is a false economy, that we should always focus on read time convenience because code is read far more than it is written. And so I basically would recommend ignoring right time convenience and focusing on read time convenience instead. One of the ideas that's come out of extreme programming is the idea of you ain't going to need it, and so don't design ahead. And as far as that goes, I think that's a very important idea. The idea that we can design for speculative requirements, requirements that we don't already know about, I think is a very error-prone practice. It tends to result in Swiss Army knife code where we're anticipating the toothpick and the corkscrew and the fish scaler and the little pair of scissors, but we don't actually get the knife part of the knife right. And I think we need to focus on getting the parts we know about right and worry about that other stuff as we get to it. That's not to say we can't look forward for requirements we know are out there, but requirements we kind of sort of think might be out there sometime. I think those are the ones that tend to be more troublesome. Modern reality number 5, the defect cost increase is alive and well. There have been a lot of assertions unsupported by data that modern practices have flattened out the defect cost increase curves. And this is just flat not supported by data. There have been decades of research up to the present day that continue to show that even with agile practices, even with extreme programming, the cost of change increases over time. And this only makes sense. If you can change one sentence in a requirements document, of course, or if you can change one sentence in a story that's posted on a Post-it note, of course it's going to be cheaper to do that than it is to rip out a bunch of class interfaces and rewrite a bunch of your detailed code and rewrite your test cases. And whether that's done all at once in a linear approach like the waterfall model, or whether it's done on a day-by-day basis where you correct the requirement in the morning and then implement it in a straight line in the afternoon, either way, the defect cost increase is a phenomenon we should care about. And the thing that has changed, I think, is that one thing that's emerged in the research over the last 10 years is that before, in the first edition of the book, I showed these curves as being symmetrical, and I think that really is not found to be true. What we find now is that architecture defects are probably more expensive on average to fix than requirements defects. And I think that's really, when you think about it, that's probably true by definition. Architecture, by definition, has system-wide implications. If you have a design consideration that doesn't have system-wide implications, it's not architecture, it's more detailed design. So if you have a defect that gets classified as an architecture defect, by definition it is going to have broad scope, whereas a lot of requirements may be quite localized, and so you may have a lot of requirements defects that can be fixed in a more localized way. So I think that's probably the major change in this over the last 10 years. And just for the record, one of the, I think, a more effective approach to trying to run projects at low cost and with high predictability is trying to correct as many defects as you can in the green zone, not waiting until the red zone. I think that's one of the reasons that test first is a good idea, because at least as far as construction is concerned, we're fixing those defects about as early in the green zone as we possibly could. And for the record, here are some citations showing the decades of research that say that the defect cost increase graph is alive and well. I've been puzzled over the years at why anyone would say this is not the case. I do think that putting specific numbers on it is not the most useful exercise, but the idea that we could fix code cheaper than we could fix a verbal description of requirements, I just think doesn't stand up to reason. Major reality number 6, design continues to be important. And what has changed in the last 10 years? Well, I've already hinted at this. In the 1990s, we were supposed to do all of our design up front. In In the 2000s, we're now hearing don't do any of the design up front. And I think both those extremes are wrong. I think that there are lots of valid points ranging from doing only a little bit of design and letting the emergent properties of the program dictate the majority of the design. That could be a valid approach. And you could also try to do the major strokes of the design and recognize that there will be some volatility, but try to do as much of it as you can. For certain kinds of projects, especially safety-critical projects, that's going to be an important strategy as well. But I think the only 2 points that are guaranteed to be wrong in every case are the 2 endpoints that the pundits advocated in the 1990s and currently. Trying to do all your design, trying to do none of your design, I think those are the 2 least effective strategies out there. I think in general we find this is true, that the extremes usually are not the most productive. Trying to plan out your entire project in advance tends not to work very well because it doesn't recognize the idea that we learn as we go and we can make better plans as we learn more about the project. But trying to improvise 100% of your project doesn't work very well either. Having some kind of basic structure for it tends to be helpful. Trying to do a pure iterative approach where we iterate on everything can, in some cases, lead us sort of down a rat hole. And we had a very interesting discussion 2 weeks ago at an executive summit that I ran. We had a major, well-known software product company that wrote off a $200 million loss and attributed it to the use of extreme programming due to the fact that they had iterated and iterated and iterated but didn't go anywhere. And that's not, I don't think it's an indictment of extreme programming, but it's an indictment of saying it was not a good fit for this particular kind of software where there's much higher value on predictability and ultimately releasing higher quality. So pure iteration can have its problems. I think straight sequential approaches like the traditional waterfall are probably more likely to have problems if you take them too much to an extreme. I think trying to say that you're going to structure everything is not a good idea because it does squeeze out creativity, but saying it should be a completely creative activity with no structure I think is just as bad. It leads to chaos and a lack of getting any kind of a closure. Same thing for documenting everything versus documenting nothing. There are happy mediums on each of these points, and it's not even necessarily in the middle. The happy medium can be 3/4 of the way to one side or the other, but the extremes tend to be the points that aren't so good. Okay, reality number 7, technology waves affect construction practices. I think one of the things that has emerged as a pattern in my mind over the 20 years that I've spent in the software industry is that we see certain patterns with technology. In the early part of a technology wave, we tend to see that the technology is not very well documented, it's not very stable. The documentation that exists contains gaps and just errors. And I think that progress is slow going. You are often the first person who is trying to do something in that technology. As you get into more mature parts of the technology wave, there's good documentation. There's good consulting support. You can find the answers you need on the web. The technology works as advertised, and so you can make more rapid progress. And then as you get to the very late stages in a technology, say banks, for example, some banks are still using DOS. I suppose maybe you know that. There you actually don't have the consulting support anymore. You don't have the vendor support. And so actually the very late wave characteristics start to look a little bit like the early wave characteristics. And I think in the first edition I didn't really want to acknowledge that construction was all that affected by technology, and I think it actually is affected by it more than I thought. But I think it also can be addressed in terms of general principles. Namely, you can think about where am I on the technology wave. If I'm trying to work on the cutting edge, then that speaks to one kind of practice. If I'm trying to work in a more mature part of the wave, then I can adopt other practices that assume a higher rate of progress and lower risk and so on. Major advance number 8, the idea that incremental approaches work best. And I think this is one thing that we knew 10 years ago, but that we have learned by experience more over the last 10 years. The pure waterfall model hasn't worked out very well. I think it's because it's not very incremental. It's not at all iterative, and I think that's really the Achilles heel. Logically, if you sort of squint your eyes and look at it, it kind of makes sense that you should try to do most of your requirements or all of them, then do all of your design, then do all of your construction. But reality has kind of come in conflict with that particular logical view, and we find that actually we can't come up with pure, correct requirements and designs without at least a little bit of iteration, and so that's worked better. Spiral development is more iterative and incremental, and so I think it tends to work better. And I think the question is not, are you going to experience some degree of iteration? You are. You'll experience it, at the end by rewriting the code 5 times, or you can experience it better by rewriting your designs and your requirements earlier, so that you only have to rewrite your code, 0 times or maybe 1 time. Reality number 9, I think, is that the toolbox metaphor continues to be illuminating. I presented that in the first edition of the book, and I'm pretty stuck on this idea. The idea that there is an awfully big universe of kinds of software out there, and there are a lot of tools available for working on software projects, and different tools are applicable for different kinds of jobs. In fact, I would go beyond saying there's a toolbox and saying maybe there's something more like a tools warehouse, and then within that tools warehouse we have certain toolboxes that apply to different industries. So if I'm in an embedded system space, I'm going to have a certain set of tools. If I'm in an in-house business system space, I'm going to have a set of tools that doesn't overlap all that much with the embedded systems world. Maybe there will be a little overlap, but not too much. And then for any particular project, I will pick the tools out of the toolbox that work best for that project. I think the things in the toolbox include things like best practices. They include things like life cycle models. Should we use spiral model or waterfall model or evolutionary delivery or stage delivery or whatnot? Certainly could include things reusable artifacts like templates, checklists, patterns, examples of past work, and of course all of the real tools that we usually refer to as tools that help us get the work done. The final reality that I would mention is that I think that there are some essential tensions in software that have remained unchanged over the last 10 years. I think that one is rigid plans versus improvisation. We are always trying to find the right balance between those two. We know that the endpoints aren't the best, but where in the middle is the best spot? Well, I think that's a moving target. I think it moves based on the project that we're working on. I think it moves based on the practices that are available. I think it moves based on the technology that's available. And what was best 10 years ago is not necessarily best today. So finding that balance point is one of the key challenges in software. Planning versus fortune telling. I think that's an essential tension as well. We would like to plan our work as much as we can, but we shouldn't pretend that we can predict the future more than we can. So how do you strike the balance between going too far and pretending you can know the future versus not doing anything and failing to plan for the things that you actually could know? Creativity versus structure. We talked about that a little bit. Both of those are important in software. We have to allow for creativity because that's what makes great products, but we have to allow for structure because that's what allows great products in a business context. And so finding that balance point is another challenge. Discipline versus flexibility. Again, we could tilt more to one side or more to the other, and finding that balance point is one of the key ways that you define not only a project, but I think an organization. Quantitative versus qualitative approaches. We have had decades of research in software that have produced some numbers about the effectiveness of software practices. Some of those are cited in Code Complete and my other books. But you have to allow for a room for people's gut as well. And there are so many variables in a software project. The idea that we could set up a detailed, statistically valid model and run a project quantitatively, I think, doesn't allow for the fact that we have huge individual variation, and managing to that the soft side of the equation, the human skills part, is important as well. Process versus product, that's a really important one. Do you focus mainly on the end game and say, look, as long as we stay focused on that, then we'll produce something good? Or do you say, look, if we follow a good process, it will produce a good result? Well, I think that there are some weaknesses in both of those viewpoints. So finding out, how much do we focus on the end game and how much process do we introduce for the purpose of getting to that end game in the most effective way, I think that's a challenge as well. And then a very interesting one, optimizing versus satisficing. Satisficing is not a word that you use every day, but the idea is that in any engineering discipline, the point is not to optimize for every design goal. The point is to satisfy the design goal. Optimization typically produces diminishing economic value. And so, an easy example is if you have a system that's producing or that's responding to the users in 1/10 of a second, you get a lot more economic value by responding in 1/100th of a second or 1/1,000,000th of a second. Well, probably not. Optimizing on that doesn't make a lot of sense once you get to the point where you satisfy. And I think this really is one of the key things that will help make software a real engineering discipline, is if we can get ingrained the idea that we need to satisfy design goals rather than try to optimize for every single one. I think the thing that has made software interesting for me for the last 20 years, I think really is these basic tensions. The balance wavers, but the tensions remain the same. If we ever got a final answer on any of these, I think that would be time for me to hang up my spikes and find something else that's more interesting to do. But I think that we will continue to struggle with where the right balance point is, and that, I think, is what makes software an interesting thing to work on. With that, I would gladly entertain your comments or questions. Yeah.
I had a question on your opinion or methods of code review during the development phase.
Of code review during the development phase. So what are my opinions on code review? Well, I have a couple of opinions on code review. In Code Complete 2, I don't have a chapter on reviews anymore. I have a chapter on collaborative construction. And I think you have to factor in practices like pair programming, as well as traditional techniques like walkthroughs or formal inspections. I guess what I think is that there are two practices that have emerged as the leading practices. One is pair programming, and one is formal inspections. We have decades of research on formal inspections. There's no other individual technique that can approach the defect removal effectiveness of formal inspections. My company's consulting experience is that when we find organizations that have had bad success with some kind of review, it's very seldom with formal inspections. It's with informal review practices like walkthroughs. And the reason is that walkthroughs too easily degenerate into poorly run meetings. And people don't generally like meetings. They certainly don't like poorly run meetings. And walkthroughs, I think, tend to degenerate into intellectual pissing contests and aren't very productive. A formal inspection, practiced pretty much by the book, where you have a moderator who's not the author of the work product, who keeps the meeting on track, who focuses on identifying defects but not discussing candidate solutions and so on. We don't find organizations disliking that. We find that it's really kind of a self-governing process. If the moderator is doing his or her job, the meeting stays on track, people feel like their time is being well spent, and so that's a good practice. And there are decades of data that say that inspections have very high defect removal efficiencies. Now, pair programming is a newer practice, and the data on that, I'd say at this point, is not entirely conclusive, but it appears at this point that the defect removal efficiency of pair programming is not quite equal to inspections, but pretty close to inspections. Close enough that you could say that a group that's really good at pair programming will probably outperform a group that's average at formal inspections. There's also some indication that pair programming is probably more expensive for what you get than the use of formal inspections, but also probably faster. That is, you don't have the wait states due to waiting for people to review the materials for the formal inspection meeting and that kind of thing. So I think there are two criteria that I'd use to choose between the two practices that I like. One is, how important is speed, development speed to you? If you're willing to trade cost for speed, then pair programming might be a good way to get to that. The second consideration is just work style. A lot of people, including me, don't really want to program in pairs. I don't want to sit shoulder to shoulder with somebody. I want the keyboard myself. I don't want to give it to somebody else half the time. And so it's not a good match for my work style. But there are lots of people out there who don't like sitting in an office by themselves. They feel isolated doing that. And for those people, it not only is a good match, but they prefer it. So I would let work style preferences have some influence on that decision as well. Yeah.
Did you look at some of the new theories in software planning? I'm thinking specifically like theory, constraint, critical chain, and the way that impacts the way that we do software development, pushing tasks closer to the beginning of the project rather than waiting to the end on the traditional critical path type techniques.
Yeah.
And I liked your comments about not over-planning or trying to over-predict stuff on it. But at some point, you do need to come down with some sort of plan.
Yeah. Yeah. So the question is, did I look at newer project planning practices? And the answer is, in my main job as the head of my software company, my software engineering best practices company, yeah, we look at that all the time. We look at it for our consulting work. We look at it in our training. We look at it in the outsourced software projects that we work on for other companies. For purposes of this book, it's kind of outside the scope of the book, I think. We focus mainly on, or the book focuses really as clearly as I can on software construction per se. But yeah, I think there definitely are some good advances there, and if I ever do an update of rapid development, that's where I'll talk about those advances. And I think we talk about rolling wave planning in our company, the idea that you can sort of plan out in detail what you can see with your headlights, but if you're driving from here to Spokane at night, you make the detailed corrections with what you can see in your headlights, and I'm going to go through, whatever, Ellensburg and Vantage and Cheney or whatever. But, you don't plan out every turn of the steering wheel and every press on the gas pedal from here to Spokane. You do that for the part that you can see in your headlights. And I think the analogy works pretty well for software project planning as well. You can map out the major points you want to get to and when to get to them, but you make more tactical, detailed corrections as you go. Yeah.
How do you notice you kind of left out a lot about doing data collection and using data to optimize your processes and optimize your defect removal and so on. Any comments on that?
So the comment is I left out comments on data collection or using data to optimize the process. Yeah, I think it's just not really the topic of this particular book. If I were giving a talk on advances in software project management over the last 10 years or advances in software process management, those might very well come up. But for purposes of this book, not so much. One of the things, by the way, I thought was interesting was that for the first edition, I read about 600 articles and books as background research for the book. And so there was a great deal of data that I found. Most articles didn't have any data, but when you read that many articles, you do stumble across some. And I was kind of surprised at how little new data had been published in the last 10 years in the construction area. There's been a lot more focus on process data, but in terms of quantitative studies on, is one style of brace placement better than the other, or is one style of indentation better than the other, I really didn't find much that had updated that in the last 10 years, which was a little bit of a surprise. Okay. Yeah, in the back.
You mentioned refactoring. Could you comment on refactoring versus bug fixing versus rewrite?
I think we should probably take this question, and then we'll have a reception. Steve will be here for another hour so that you can ask him in person, and otherwise we should let the big audience go.
Maybe we should just take that question in person. Okay. So comment on refactoring versus bug fixing versus rewrite. That's a pretty broad question. I'm not really sure what to do with that one. I kind of told you that I think refactoring is a nice discipline when practiced by the book, not so nice when it's a synonym for sloppier practices. I guess I don't have a whole lot to add to that at this point. Okay, thank you all for being here.